Hi, in this video we're going to be talking about section 13.1, which is all about vector functions and space curves. So the first things first, let's define what a vector function is. The idea is that a vector function is going to model the position of a particle in space. It can obviously represent other things. You should be used to it from a calculus course, that if we can have a function modeling the position, we can also have a function that models the acceleration or the velocity or many other things. But the most practical application would be a function that shows the position of an object in space. In that way, they're very similar to parametric equations. And in fact, we are going to use some of the same notions we had from parametric equations, such as we have x equals a function of t, and y equals a different function of t, and we call t the parameter. You might be able to see where this is going. If we're talking about a 3D vector function, and we would like to talk about multiple dimensions, then what we would want to do is look at, I guess in 3D, we'll have a function for x, a function for y, and a function for z. And each of them will be seen as the output of one independent variable, t. These three will be called the component functions. They are parametric equations after a fashion, but we also will call them component functions. And then r of t, notice I'm using vector notation, f of t in the I direction plus g of t in the j direction plus h of t in the k direction, or simply written in component notation, cough, 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 f of t, g of t, h of t would be called the vector function. So r is a vector function, or sometimes we call it a vector valued, because we can see that the output of r is a vector. It's going to get a scalar input in each of these three components, and it's going to turn into a vector. To put a fine point on it, the terminal points of the vectors r of t, like once we graph all of the vectors, so to speak, of this vector value function, if we graph all of the vectors, their terminal points will create a space curve, which is really just a path through space. I'm going to warn you right now, it's not really a surface. We're going to talk much more about surfaces in chapter 14. You saw some surfaces like cylinders and more complicated surfaces in chapter 12. Chapter 13 is just showing you a different kind of thing that can happen in 3D, where we're not talking about a surface, we're talking about a path, a space curve. So we're not talking about something that has width and breadth like a sheet of paper. We're talking about a line will be an example of this, you'll see. Or we're talking about a curve. I'll draw a picture on the next slide. Not a surface. These paths will be on surfaces. The curves we can say lie on surfaces, but they're not going to be surfaces themselves. A vector function is a parametrically defined parametrically defined function where the terminal points trace a curve in 3D. And just like with parametric equations, T will give, or sorry, the domain of the parameter, again that's T, will give the curves an orientation, like a start and an end, although it doesn't have to be that simple. Just a direction to them, so to speak, right? Like we don't have to necessarily have a start. Like the curve doesn't have to start at a specific time. It does not have to end at a specific time, but we have an idea of times arrow, that there will be a before and a later. So if we draw our axis system and we start tracing out some of these vectors, and they're all going to be position vectors starting from the origin, and we just want to look at the terminal sides, what we might get is a curve that defines the position of a particle flowing in space. And again, what we'll have here is an orientation. It will flow just like, a particle moving through space. That's why a lot of this calculus was initially developed, was to help describe the motion of planets, of other physical bodies. So if this is a function, we want to be able to talk about its domain. So let's talk about the domains of these vector valued functions, or like a general example. So we're going to have r of t equals root t 1 over t minus 1 and a natural log of t. Okay. The main thing I want to say here about the domain is that the domain of this vector value function will be the intersection of the domains of the component functions. So for this case, we have 3 component functions. And it's very useful when we're studying this to be able to understand that x, the x positions are given by root t, the y coordinates are given by 1 over t minus 1, and the z coordinates are given by natural log t. And so I'm saying that each of these guys has their own natural domain. Sometimes you'll be given the domain explicitly, but when you're not, you have to understand what are the domains we're finding. So, specifically, if we have square root, we'd want t to be greater than or equal to 0. A rational function, we are only worried about a 0 in the denominator, so t cannot be 1. And for natural log, we want t to be greater than 0. We cannot have 0. We can't have 0 either. And we need to keep everything positive. One strategy I've seen some students like to use is a number line sort of strategy. So clearly 0 and 1 are important pieces here. We can't have 0. We can't have 1. So I'm going to put open circles. And where else are we allowed to have? Everywhere greater than 0, but we're skipping 1. And so if I try to describe the domain of R, domain there's a couple ways to describe it. In interval notation, it would be 0 to 1, not including 1, and 1 comma infinity, again, not including 1. You could also say t greater than 0, t not equal 1, if you were using inequality notation. And that's really all there is to it. If the number line helps you, if you have trouble seeing the intersection of these domains, where they're all okay, the number line might help you. So I'm going to say, why don't you try this one? Example where r of t equals t cubed I hat plus natural log 3 minus t j hat plus square root of t k hat. Try to describe the domain of this function as best as you can. I'm about to do it. 3, 2, 1. So if x is supposed to be the I component stuff, and y is the j component stuff, and if you got this wrong, you should try again now that you know what the correct x, y, and z are. The domains of each of these would be all t, all real numbers. Here, if you haven't seen this in a while, it would be 3 minus t has to be greater than 0, which would be, that's the argument of natural log, which would mean that t had to be less than 3, strictly less. And here, t has to be greater than or equal to 0. So in some sense, we're trying to come up with the most restrictive domain. We only want to use the values of t that work for all of them. So here's one more time why this number line strategy might help you out. So put the key points on the number line. And if you have highlighters, it's going to work really well. So our first guy is really okay with everybody, right? Not useful. T less than 3 would be like open and going that way. And then t greater than 0 or equal to would be a solid dot on 0 and then going that way. And we're trying to see where were all 3 satisfied. Where are all 3 of these functions satisfied? And there's only one situation. Again, some people say all t here. That's not true. We can't use all t for y. We can't use all t for z. We can only use our domain for r of t would be 0, including, up to 3, excluding. Or greater than or equal to 0, less than 3. That's the intersection of the domain. So when we have something like all t, I'm just trying to say this one more time, when we have something like all t, it's not doing anything in the intersection. It's not telling you what we have to leave out. Okay? He goes along, he gets along, that kind of thing. In terms of plugging values in, there's not much to see here. If I wanted to find out what is r of 0, we would just get 0 I hat plus natural log 3 j hat plus 0 k hat, right? Not very interesting. Not very interesting at all. Again, you could write that in component form. In some sense, this is the initial coordinate. This is where we're starting from because it's inclusive. And r of 1, just to be clear here, talking about 1 I hat plus natural log 2 j hat plus 1 k hat. And I guess just to show you that things don't have to be the same in the I and the j component, at 2, we'd be getting 0. Natural log of 1 is 0. plus root 2 k hat. Okay? We'll talk about how you might start drawing some of these. A lot of these will not be easy to draw, but we'll definitely talk about the theory of drawing them and how we can think about how these paths move along surfaces. Want to talk about limits and continuity. The main idea here, I would say, is it works how you think. I know that sounds a little silly. The limit as t approaches a number a for a vector function r of t is going to just be the limit of the x component, f of t, in the first coordinate, the limit of the g component in the second coordinate, and the limit of the h component in the third coordinate. You'll just do the limit of the three functions. It's incredibly easy and basic. For instance, example, limit as t approaches 2 of root t I hat plus t squared minus 4 over t minus 2 j hat plus t over t squared plus 1 k hat. We're just going to find the limit of each of these three. You don't normally have to write all this out, folks. What's this limit? Root 2. If you can do these in your head still, good for you. The only one I need to review on this one is maybe this. If you plug in 2, we know we're getting 0 over 0. That's a problem for us. If you're really ambitious or forgetful, you might use L'Hopital's here. It's simpler than that. I would say this is a technique that you would have before L'Hopital's. You would factor and notice that it cancels out in this fashion. So this is going to 4. And then the limit of the k component. That guy's continuous. That's one thing I'll be mentioning in a second. So clearly this is going to 2 over 5. Plugging in 2 works fine. That's been our strategy for limits since calculus. If you can plug in the number, it works out nicely. So what limit are we getting? Root 2 I hat plus 4 k hat. Nope, 4 j hat plus 2/5 k hat. Easy peasy. I'll do one more just to go over the situation here in case you forgot one of our trig limits. You might want to try this out and see how you would do with it. So what if I said find the limit of as t goes to 0 for one minus t cubed, 1 plus, I think I meant, t e to the negative t and sine t over t. See what you remember about limits. There's definitely some issues and some forgetfulness. Okay, so I find that in this case it's really easy. The first one, 1. The second one should be 0 because we have 0 times 1. If you thought it was 0 over 0, you'd be forgiven. The last one, 0 over 0, right? This is going to 0, this is going to 0. But in general, if you do L'Hopital's or you remember the rules for sine over t, sine t over t, also going to 1. I guess I never said anything about continuity, but R of t in general, not this R of t necessarily, is continuous if and only if, that's an abbreviation for if and only if, f of t, g of t, and h of t are continuous. So a quick example of that would be something along the lines of where is r of t equal 2t over t squared minus 4 I hat plus sine inverse or arc sine t j hat plus cube root t k hat continuous. So where is this continuous? You would start, just like we did in Calc 1, by finding the domain. Let's talk about the domain of each of these functions. You should try that out right now. So this guy, his domain would be t cannot be 2 or negative 2. Arc sine, this might be a little tricky for you. We're thinking about what numbers can go in to arc sine. Sine inverse is the same as thinking about what numbers come out of sine. So for sine, we get all the numbers between 1 and negative 1 as outputs, as the range. And the range of sine becomes the domain of sine inverse. And for cube root of t, we have all t. Again, putting these together, you would see that the domain of r of t, what's the most restrictive we can be? What are the only values of t that'll work for all of them? It's going to be negative 1 including 1. This will get left out. We will exclude these two problems if we stick with this. We can't go to 1.5 or anything because then we would be leaving that guy out. And each of these functions are continuous on their domain. Remember that. On their natural domains, functions are continuous, meaning this guy is continuous everywhere besides 2 and negative 2. This guy is continuous everywhere besides, on that interval from negative 1 to 1, and this one's continuous everywhere. Because continuity is the nice property. I'm not saying R of t is differentiable. That's something we'll look at later. Domain of R of t is this, and so continuous on domain is the main idea for here. In the next video, we'll take a look at how to sketch these curves. Thanks for watching this one. See you next time.